But yeah, without further ado, let's introduce the next speaker, Katie. So for those of you who don't know, Katie is a bug bounty hunter, educational YouTuber, and is somehow finding the time to finish her PhD in cybersecurity and machine learning. A former data scientist turned cybersecurity person who's been in bug hunting until 2019. That's her bio. Today, Katie's going to be talking with us about an intro to AI for bug bounty hunters, which I'm super jazzed for this talk. I think this is going to be super informative and exciting, not for the least of the reasons to actually understand what AI means and is, hopefully by the end of it. So take it away, Katie.
Well, thank you for having me. Today, I'm really going to be talking about several different topics, but I hope you'll come away from this entire introduction thinking, I kind of understand this a little bit better. AI and machine learning as a field moves really quickly, and sometimes actually quite slowly. And there's a lot of terms. So I really hope by the end of this presentation, you'll maybe understand a little bit more. So I should start by introducing myself again. My name is Katie. I call myself an occasional bug bounty hunter because I don't always have the time to do it part-time. But I'm part-time a cybersecurity YouTuber. I make videos on bug hunting on YouTube. But that's kind of what I'm well known for. But actually, I also have a day job. I'm a PhD student, and my PhD is in cybersecurity and machine learning, and I have a bachelor's in computer science. When I finished my bachelor's, I ended up working as a data scientist. And if you don't really know what a data scientist is, it's kind of like the software engineer for things like machine learning, but also a bunch of other things. My job in machine learning was not actually that interesting. I did kind of got a bunch of sales data and worked out which salesperson would sell what data the best. Sounds really boring, was kind of boring. That's why I'm a PhD student now. So we really want to start with one key question, which is, what is AI? And I'm going to tell you probably everything you might have ever wanted to know about AI. But let's start with the big question. What is AI? And I think this is a really great way to explain what AI is. It's this kind of ever-increasing circle. We start with AI, which is this general concept of a program that can sense, reason, act, adapt. We think about a machine that can act like a human. Then we have machine learning, where we have algorithms that are specifically designed to improve their performance when they're exposed to more data. And then we have deep learning, which is about neural networks. But if you're not really familiar with these terms, you probably don't really understand them. So I've created this in memes. Now, our big AI is if statements. So this is quite a big meme that all AI is just if statements. Then we have machine learning, which is just statistics that we rebranded as machine learning. So statisticians would get upset. And then we have deep learning, which is really importing a program called TensorFlow into your code and making it do all the hard work while you sit back and do machine learning research. So this is a bit tongue-in-cheek because it's not always if statements some of the time. So AI is this gigantic field, but it includes a bunch of other things as well. So we have machine learning, which is kind of separated into supervised and unsupervised. Don't worry, we'll cover that. Then we have natural language processing, which is what I do for my PhD, which is all about kind of statistical analysis of text and human language. We have computer vision. That's, the self-driving cars that can see if something's a human or a dog or a stoplight, whatever. But also those memes where you see, like, why is my machine learning algorithm recognizing a dog as a cat? That kind of thing. And we also have our if statements, so robotics, manufacturing, optimization, which might kind of look like machine learning. That is if statements most of the time, if statements all the way down. And it's not always the stuff of nightmares. So this is a neural network, and it's designed to kind of replicate how your brain works. Apart from it doesn't do that, it just gives you nightmares of these kind of like inner layers, which will have all these neurons that connect. Now, I'm going to reassure you here. Machine learning is just statistics. If you have a bag of balls, and if I pull out 3 red balls and 1 green ball, the probability of the next ball being red is 3 out of 4 and being green is 1 out of 4. Now, this doesn't really matter because it could be that the next all the other balls that say there's 10 balls in a bag, the rest of them are also green. So we really can see that the probability of it being green might be 1 out of 4 based on what we've seen, but actually the statistics might not tell us the full story. And from this, we kind of make a prediction that a red ball is most likely. It could be the rest of the balls are green. However, a red ball is more likely. And this is primarily what AI is doing under the hood. It may look like AI is doing all these clever things, but really under the hood, AI is just looking at these statistics and kind of making predictions based on what it's already seen. Unfortunately, machine learning is just statistics. And the field of statistics has moved on since you did kind of maybe grade school level stats, where we're talking about balls and bags. And no joke, this is actually an algorithm that I had to look at for my PhD. And I had to explain. I was like, I'll just look it up on Wikipedia. How does it work? I looked at this and thought, okay, for further information on this algorithm, please see paper name, year, because I'm not going to touch that. And often in machine learning, the maths kind of looks much closer to this. We're not maths people. This looks confusing. There are like Greek letters in there. No. We're not really looking at improving the algorithms, and we really don't need to know all this. We really only need to know the kind of what the algorithm does and how it does it. So what is the core of machine learning? Now, there's 2 kind of key concepts here. One is training a statistical model on a bunch of data, and then using that model to make predictions about new data, using what is previously seen to make predictions about new data. And that is all machine learning is. Like everything you see from computer vision to self-driving cars to what might be the next bug hunting machine learning model, it's all going to be data, model, prediction. It's not going to be any more complex than that, I promise. So I told you about the statistics, and I told you that's not really what it looks like. So let's have a chat about practical machine learning. So I'm kind of skipping over here the other types of AI. I'm focusing on machine learning because it's one of the easiest to explain. It's where most people start. And machine learning can kind of be broken down into how the algorithms work. And that's supervised, unsupervised, reinforcement, and something called semi-supervised. Now, that doesn't mean that they need a programmer watching over the algorithm all the time. What it means is that the data has labels associated with it. For certain like supervised machine learning, I'm going to give you a bunch of data and give you the label. So that might mean I give you a bunch of photos and I tell you this is a duck, this is a duck, this is a duck, this is not a duck. And then I ask you to predict which one is a duck, a new image. And then unsupervised is where I give you a bunch of pictures, don't give you any other information, and just tell you sort them out. Reinforcement learning is a little bit different, and it's primarily used in kind of different fields, but I'll explain that a little bit more as we get to it. But it's the idea of rewarding an algorithm when a model works really well. And these are all used to solve different problems. I really like this graph over here. Because I think it does a great job of kind of highlighting it. So we have in unsupervised learning, we have clustering, we have recommender systems. So that's when Amazon tells you a bunch of products you don't want. Customer segmentation, so that's when you kind of look at a bunch of customers and decide which categories they go into. Over in supervised, we have image classification. And over in reinforcement learning, we have game AI. So they're used to solve different problems. So I want to just go into sort of more detail on what these look like. So this is supervised machine learning. Now, we give it a bunch of pictures that have labels, and we ask it, new image, tell me what it is. And this is one of the simplest forms of machine learning you tend to see. A lot of kind of complex machine learning is built from these statistical, like supervised learning models. The problem is that, as you can imagine, you need a lot of data to make machine learning work very well. And not just that, you need a lot of labeled data. And humans have to make those labels. You can't get a machine to make the labels for you, really. And it won't be accurate if you do. So not only is there just like the whole getting all the data, you have to label all the data. It's quite labor intensive to do supervised machine learning. But it works great for classification problems. So when you have like, what is this? Is this a cat or a dog? Is this a duck or not a duck? So that's the first kind of easy kind of beginner stuff. We then have unsupervised machine learning. Now, as for supervised machine learning, where we had a bunch of data, labels associated with each piece of data, with unsupervised machine learning, we have the opposite. We just have data and we ask the machine to figure it out for itself. Now, the way it does this is quite interesting algorithmically. I won't kind of go into that, but it tries to draw these boundaries between where the data might be. You tell it how many clusters it needs. So in this case, we've asked the algorithm to take this data and turn it into 3 clusters, and it kind of decides where those boundaries might be between the data. Now, this is really useful, and this is like what I do during my PhD as well, because this is not very labor intensive, comparatively anyway. You just give it data and you just see what it figures out on its own. It's only really can be used to solve some problems though, and what it's good for is really going to be dependent on what problems you have. Very, very good for clustering data. Kind of a good security example might be, I have a bunch of bugs, tell me which bugs have some kind of relationship. You know, tell me where SQL injection is related to blind SQL injection, for example, which is related to whatever. And then we have reinforcement learning. And this is my favorite example. And I don't know if you've seen this. This was quite popular a few months ago. And it was on the BBC. And what this is it's a skeleton that's got some rules associated with it, with how it can move. And it learns to walk and jump and run in a very strange way, because what happens is the algorithm gets rewarded the further it can make it. So it just basically hits random buttons until it makes it further. Then it tries to almost mutate that. So that's kind of very similar to what we might consider as evolution, but not as we know it. Like, it's very different. It's kind of like watching it play, what was that game? Q-Op? A few years ago, where you have the like runner and you have to hit the buttons and you just end up hitting them randomly. So we know the algorithms now. How do we actually train them? So once we decide an approach, we need to train the algorithm, which seems simple enough. You'd think one line of code, model.train, put your data in, sorted. Actually, the actual stages of going from data to machine learning model is quite difficult. There's loads of stages, and in each stage, it really does impact the performance of the model later on. So it's really important to make sure you get it right and kind of have this iterative process. So some of the stages you typically see, splitting the data into a test and a train set. I'll explain that in a sec. Selecting which features are the most important. So that means, you know, what part of a duck makes something a duck. And then evaluating the model. Does it work well? What's the accuracy like? Now, accuracy when it comes to machine learning, I'm going to use it very generally. I am aware that there are measures of accuracy and there's loads of different types. I'm going to cover that. That's fine. So let's talk about splitting the data. So when we have developed these machine learning models, we have our training, but we also have to have some way of seeing if it works. And then primarily, like, the way we do that is we take our big data set and we just go 80% of the data will be used for the training of the machine learning and 20% will be used for testing later. There's a big advantage of this, that because, say, for classification, we know what labels they're associated with, we can kind of see, you know, we can tune the model a little bit, change some hyperparameters, which are like hidden parameters in the model, and then make some small adjustments. Does it work well? Whatever. And then for some, you might have not just a training and test set, but also a validation set. So you might be starting with, say, 100 records. By the time you do this, you might be only looking at 60 records that you can actually train your machine learning model on. So you end up like slashing the data continually just to try and get something that you can test. And you can validate and you can see if it works. Feature selection is next. So feature selection is all about what makes that piece of data that class. Because we might look at a duck and compare it to a cow and go, well, a duck has feathers, but actually all birds have feathers. And that's not really something that's special to ducks. It's just all birds have feathers. You go, oh, well, it has a beak and its face is green. And then you go, well, you know, does other things have green faces? So when you do this kind of process, you're really trying to pick out what is the most important features that will lead to the best classification overall. Because if you include everything and you go, well, I'm just going to train on everything, what you'll get is something that takes ages to run and that won't give you any good results. It will just return garbage. So we've got that. Then we've got evaluating the models, and there are so many different mathematical ways of evaluating models. There is tables of accuracy, there's per different algorithms, there's different ways of looking at things, there's heuristics, there's precision recall, there's R-square. There are so many ways of like quantifying if something works, and actually this can take a really long time, because you have to figure out when you actually okay with your model being bad, because you won't get 100% accuracy. You may not even get 90% when you first start out. It's working out kind of the best combination, best recipe of data plus hyperparameters plus the test and training sets plus whatever that ends up giving you the best model possible. And with that comes errors. And one of the biggest errors we see in machine learning is bias. Any machine learning system is going to be biased towards the data it was trained on. And often the data comes in biased. So, for example, GPT-3 can't give you a sentence about Muslims without it being about violence. Apple's credit card system was discriminating against women. Tay tweets, which was this famous kind of experiment set up by Microsoft, people tweeted out racist things to the robot, and the robot tweeted out racist things back. It learned from what people were tweeting at it. When you give a image classification system pictures of people cooking, it often assumes they're women because it's seen more women cooking. On YouTube, if you post content that's LGBT, you're likely to get demonetized. And we kind of wave this away as garbage in, garbage out. It's really important to know what the data is trained on and how that's actually going to affect the model, because, you know, these are really extreme examples that are quite well publicized. But if you've got a model that's only slightly biased, you're going to have similar problems. You're going to have errors, and you're not going to be able to really fix them. Not in the same way you can fix code. So it's really important when we think about errors to also think about what you've actually fed the model and what data it's got. So that's a very, very quick introduction to machine learning and kind of some of the relevant issues. And if you listen to this part of my talk and you go, yes, that sounds amazing. How do I get into that? The best place I find to go is DataCamp. Machine learning kind of models and code is often written in either R or Python. I'm going to guess and say most people here want to use Python, not R. I did a survey on this, and I was very much not in the majority with liking R. And datacamp.com is amazing for this. And if you want to have a go at kind of doing this on real data, Kaggle.com is bug bounties, but instead of finding security vulnerabilities, you make machine learning models. Same idea. You get paid. There are people talking and doing write-ups about how they built their models. So I just kind of want to take this and talk about how you build a model, a step-by-step guide. Step 1, your data. Step 2, you've got to understand the data. You can't just take the raw data and run it through an algorithm, because all that will give you back is terrible results. You've got to understand, you know, is this biased? What issues does it have? What works really well? what might be a good predictor. Then you have feature selection. So you look at every single value in the data set and you look at the ones which are going to provide you the most accurate results. You build a model. In this case, this is a decision tree model. You test the model. You test its precision, its recall / sensitivity, selectivity, accuracy, F measure. You do a bunch of these maths, and you build the model again because your first model was probably bad. You test the model again, and you use the model on new data. So you build this model, you apply it to new data, and then you get results back. And you know what that gives you? It gives you more data. And this is how you have this iterative process of designing machine learning models, where you kind of end up in this sea of data, and really your job is to kind of wade through it and find meaning in that data and take that meaning and show how you can use it to really build and understand and create these machine learning models to predict more. So, okay, what about bug hunting? And I'm going to call this AKA why we won't see AI taking over bug hunting. I hear this a lot. A lot of people are very worried that AI is about to take all of the bugs. And I really want to reassure you with this. AI is not going to take all of the bugs. You're going to be fine. So really, when we look at machine learning and cybersecurity, apart from vendors who are often bragging about their amazing machine learning algorithms, a lot of it is still far more in academia and academic spaces and isn't necessarily being operationalized, because it's actually quite difficult to operationalize machine learning, especially in something like cybersecurity, where one of the big kind of issues is like regulation and being certified for things. And especially when we start to consider, okay, could we build machine learning models to hunt bugs? The research just isn't there yet. We don't have like any of the people working on this. So do we need to worry about AI? No. Why don't we need to worry about AI? Statistical models need data. It's so important. You cannot build machine learning without very large data sets. You can do it on small data sets. It just won't work. It won't be accurate. It won't represent reality. It's just not going to work. And there is no publicly available data sets on how people approach hacking. Specifically, you know, what people need to do is record what steps they take. So then we could figure out a way to represent that and then kind of recreate that as a machine learning model. It doesn't exist. The data isn't there. When we think about the evolution of machine learning, and kind of before we build up the data, we have to kind of go through these stages. We start out with a sea of data. We then have to figure out, you know, how can we look at it? How can we get meaning from it? So if we think about that with the Lego bricks, we have a pile of Lego bricks. When we sort the Lego bricks, we learn more about them. We can see every single color that is there. When we arrange them, we understand more about what shapes are available. And then when we present them visually, we can really start to understand, okay, we have a lot of yellow and red. It's not until we get to that final step of seeing it visually that we understand the data we originally started with, which is a lot of red and yellow bricks. So before you build the model, even if the data existed, you have to understand the data itself. And machine learning cannot recreate human creativity. A lot of people worry about like general AI. It's nowhere near that. There's no way an AI can accurately represent human creativity. It slaves to its data it's trained on. It can't think outside the box. It can't produce something new. It has to go with what humans have already told it. So the data isn't there. Even if the data was there, we don't really understand the data. And even if it was there, we still couldn't find unique bugs. It would just be a slave to the bugs it's seen before. And really one of the big things the community is missing is expertise. Now, I hope by listening to this, you kind of realize how much effort it is to actually make a good machine learning model, because the actual cycle, and I think this is a great idea of how machine learning works when you start to think about it from like a deployable piece of software. We need to understand the business. We need to understand the data. We need to prepare the data, model it, evaluate it, and then we can deploy it. The problem is throughout all of this steps, these steps here are a cycle of, and like slightly more and just like better understood. Even if you have all the data, even if it's all labeled, it's really easy to build a bad model that doesn't work. Okay, what do we have and what are the next steps to be able to do machine learning? We have bounty targets data. Now, this is a data set available on GitHub, which has a list of all the domains on HackerOne, on BugCrowd, on I think it has Integrity now. It's got all of the domains and what's in scope. And this is a good place to start if you want to see kind of what websites are available and look at the domains associated with them. We have bug bounty scans, which is just scanning results of different domains that are available on bug bounty programs. We have awesome bug bounty write-ups. If you remember right to the beginning of the presentation, I talked about natural language processing, the ability to understand text. So something written in human language like a write-up, could we potentially try and retrace the steps? I don't know. It hasn't been done yet. We have the official HackerOne disclosure timeline. Again, list of disclosed reports written in human language. That's something we can look at doing next. So the next steps for AI and bug bounty. One is we've got to understand the data we have. Now, usually we do that by conducting an exploratory data analysis. We look at the data and we just visualize it in a different way. We give it a poke and see what comes out. We need to understand what our goals are when we want AI and bug bounty. Do we want to be able to find bugs? Do we want to be able to do recon activities? Do we want to kind of, I don't know, look at, see what bugs are going to come next, what bugs are going to be the next big thing? We need to gather the data. The data isn't there for most of this. We need to find it. Even if we want to automate the finding of bugs, we need to record how people hack. We can't do that part unless we have the first part of recording people hacking. And it's only once we go through those steps, we can even think about machine learning methods and models being applied generally to this space in the field. We can't look at it now. We've got to do all these other stages, at least until it works properly. Because there's just no way to get an operationalized machine learning model in the space of time that kind of we're looking at the moment. But you know what? If you can't join them, beat them. You can hack machine learning. This CVE was issued in 2019, and this was this piece of research actually done by a member of the AI Village at DEF CON, who found it was by looking at email headers, they were able to create a copycat machine learning classification model and then extract how their model worked to try and craft emails that would get through filters. This is from a really great paper talking about what the attack surface of machine learning algorithms might be. We have kind of issues in feature extraction, prediction, cost function, minimization, model representation, and clustering. And we have a bunch of these kind of exploitation techniques and impacts, which come to some of the bugs we can find. Even if we're looking at machine learning models, you know what we can find? We can find arbitrary code executions. We can find denial of service attacks. We can also corrupt machine learning models by giving it fake JPEG files. We can cause memory corruption. Actually, machine learning is becoming more and more popular, especially with like big organizations who are desperate to have the next shiny new thing but don't really understand the security issues around it. This is not something to be afraid of, my friends. This is something that is an opportunity for us all. So thank you very much for listening. If you want to follow me on any of my platforms, my YouTube is InsiderPhD and my Twitter is InsiderPhD. You can Google me. Thank you very much for listening, everybody.
That was fantastic. I really do encourage people to dig into your YouTube as well. I know at any part of the journey, there's a lot to get out there. I've been recommending videos and intro, for people starting out, but I know even as someone who's done it for a few years, I get a lot out of your content. I think it's brilliant. But
thank you.
Before, I'm going to be a little bit selfish here before we dig into questions from Discord. I have a personal question I wanted to ask. You were saying about it's very difficult to operationalize because of lack of data. Do you think on the inverse of that, there's still a lot of room for defensive team to take the data that they're receiving from organic traffic to start to filter out malicious traffic easier? Or do you think it's too noisy for that to be a productive space?
So there's a lot of research on those kind of steps. I don't know if there's anything we can do about traffic, because in general, it's quite difficult to do anomaly detection on traffic because it is so noisy. One thing that blue teams could do if they have a bug bounty program is actually try and gain insights from reports that have been submitted and then make changes to their program. If they're seeing a certain class of bug, maybe they can do internal testing for it. I'd be disappointed because that means I would get less bugs. But things like that are like a total way that a blue team could kind of not necessarily exploit their own systems, but use the same data to solve a different problem.
Yeah, that makes sense for sure. And I guess to flip to one of the YouTube questions, is there a way to use machine learning with reinforcement learning to follow the pattern of hacking to find exploits? So could you monitor your own traffic and use that for an exploratory path?
That's a great question.
So I don't know, because the research hasn't been done. And you know what that means? That means that you can look at it and do that research and see if it works. This is really the first steps. And I'm delivering this presentation and I'm really giving away all my ideas here because there's a lot of stages that one can take to really kind of push it forward. When it comes to using reinforcement learning, you still need quite a lot of data. And the question would be, how many people are you recording? How diverse are their hacking techniques? If we're just going to be doing the kind of traditional reinforcement learning, which is hitting a bunch of buttons and then rewarding it when it gets that far, are we testing it on CTFs? How are we rewarding it? What kind of reward scales are we looking at? There's so much there. And you know what? You can do that research. You can find that out.
How much, from your perspective, working on this stuff, in context of your PhD and professionally, how much does it rely on the target being the same? Because I would think that the other thing that would be a challenge, behind the idea that is in the question Michael just asked, is that every target is different as well. You're not just talking about one CTF, framework or one, Windows box on the internet or whatever. It's just a whole raft of different stuff.
It'd be really difficult. I think when it comes to what we're really asking machine learning to do when it comes to like finding bugs, I don't know if we're there yet. I don't think we have the openness of how kind of like pros especially approach targets that they would be willing to share, because that's proprietary, like that's essentially their job, and they shouldn't be forced to share that. I should say I'm not against them. That's totally fair for them. But I think that represents a real barrier to getting that type of machine learning. However, there's a lot we can do with the data we already have access to. We have HackerOne publishes a ton of disclosed reports. We have people who do write-ups. We have bug bounty tips on Twitter. We can't just think of what we might think as like our perfect AI system as being something that can hunt for bugs, but something that can do, say, automated recon might be a really nice first step in doing this kind of task, but in a little bit of a different way.
Yeah, it's interesting. And switching gears to offense, just talking about that a little bit more, because I think, when I think it was the last stream that you and I were on together, when it's like, oh, we should talk about AI through this lens of, and ML specifically through the lens of the fact that like we've gone and slapped it on just about everything we can think of as the collective internet over the past 10 years. And what tends to happen is when that sort of product development happens, you find out about 5 years later that you forgot to do anything meaningful when it comes to security. So, when you're talking about actually attacking machine learning, what are some of the things that you're seeing be effective? How do you think about that? I mean, even as a hunter.
So there's a really interesting question in machine learning at the moment in general, which is what is a bug when it comes to machine learning algorithms? Because we accept machine learning algorithms will make mistakes because they're not perfect. Oftentimes they might misclassify something. But here's the question. What time is a misclassification of something a bug? If we look at, say, image recognition, if we think about our classification algorithm confusing a dog for a cat, no big deal. If we confuse it for not being able to recognize a person, it's a self-driving car. That's obviously a huge risk. And what part of poisoning the algorithm can we do? And this is kind of a discussion that happens within the community at the moment. Like, what is a bug? What isn't a bug? What's a bug we can actually exploit? One thing that I think is really interesting is kind of the combination of machine learning and business logic, because machine learning plays this really interesting part in how applications work nowadays. And if you can kind of break the kind of flow the same way you can do with other bugs, by getting a misclassification, that can be a security risk depending on where it appears. You don't always look for traditional security bugs. Sometimes you have to look for something a little bit different because machine learning works a little bit differently.
Yeah, I mean, the thing I've always found fascinating about that is the idea of, it basically being untrusted input. Like anyone who's worked in security for any period of time, the alarm bells immediately start ringing as soon as you see anything that looks like untrusted input. And the quintessential example is I think it was Israeli research where they spoofed the GPS coordinates of a bunch of Android phones to basically cause a pseudo traffic jam on the peninsula that ended up rerouting traffic. And then just
Which
recently,
is a really interesting type of bug.
Yeah. Well, another guy did it just recently in Europe somewhere. I can't remember exactly where, but he got a bunch of phones, put it in the back of a little red wagon trolley thing.
Yeah, I saw that.
Walked really slowly across a bridge. It's like that's technically a machine learning attack. It doesn't fit into, I think, the normal paradigm of computer science that we tend to think about in bug bounty, but it is basically exploitation of a assumption in a model that's not resilient to that type of abuse.
Yeah, and I think to add to that, not only do we see these kind of new attacks, we still see the same bugs. Machine learning is not impenetrable. If you have kind of dealing with images, dealing with kind of any kind of pre-processing, you're going to hit like the traditional exploits of, XXE or anything where you're messing with entities. You're going to find the same bugs. Mess with image, you might hit image magic, for example. So really, we both have to think about it as not being that different, but also not being like the same, which is a really interesting space to be in, I think, especially as kind of this is being more operationalized now in actual like vendors and stuff.
It's very cool.
So if we're going to move down this path of taking advantage of AI, what sort of data sources would need to be available, or what sort of data would you look at to start training the models?
Oh, there's so much you can do, and it's going to depend on what your expertise is. I am an NLP person. I think language is really cool for machine learning, and I'm going to go off and lovely rant now. The primary way we kind of communicate with each other and we interact with the world is through language. We talk to each other, we write long documents. If we want to share our knowledge, we use language. And that means it's a great place to train machine learning algorithms because actually it contains a lot of information, especially technical information. Now, I am an NLP person. My first instinct is let's look at the disclosed reports. We have loads of disclosed reports. We have a bunch of bug bounty write-ups. What can we learn from those? Let's look at doing kind of an exploratory data analysis on what data we have. How can we graph it? What kind of information do we have access to? How can we use it? That'd be my first kind of step. Somebody who has computer vision background might say something else completely. They might go for another type of looking at kind of behavioral, seeing if you could record what people are doing in some way, that kind of thing. There's a lot of ways you can do it.
Yeah, I wonder if a computer vision person might even just take screenshots and look at the screenshots and determine what to do in a particular application just from screenshots.
Yeah, and especially if you look at when people tend to have like include a POC, include a screenshot as well of what they did, you know, how much can we learn from those? There's so many different ways to think about this. We really are like infants. We've got so much further we can go. And I would like, if you're listening to this and you found what I'm saying is really interesting and something you want to pursue, go and pursue it because nobody else is. And there's a lot you can do with what we already have access to.
That's awesome. There's an interesting question that's kind of come in from YouTube. In what you've experienced with different models and talking about different exploits, have you seen any where you can essentially DOS the intake with a large image or a large data flow? Like, are there many input validation kind of bugs that you're experiencing, or are they more in manipulating the outcome of the data themselves?
Oh, input manipulation is one of the primary bugs you see on machine learning at the moment, because where a regular application might only have one stage of processing, there is so much that happens with a machine learning. It might go through, go in through a web server, go into a Python script. The Python script then gets piped into something like Go, and then the Go script gets piped into R. And you have so much like when you hit those kind of boundaries, you have another language of bugs to look at. So I think it's really important also to consider that machine learning algorithms tend to be written in R and Python. So if you want to if your application isn't written in R or Python, most aren't, you're likely going to be in a position where you're having some kind of like translation between the two pieces of software. Great place to look for bugs in that little gap.
That's awesome. So, yes, I guess kind of taking a step back from bounties as well. Do you see like competitive CTFs? Do you see machine learning starting to take a rise there, or do you expect it to start to take a rise in that space where data might be a bit more constrained and available, but provides you a reasonable degree of advantage?
I can see it, but maybe only in particular areas. Even the kind of big companies tend to focus their machine learning efforts in separate areas at the moment. We don't necessarily somewhere like Google is maybe going to focus on NLP because they have Google Translate. They have a lot of search functionality that requires a lot of NLP experience. You'll have NLP people heading into the kind of security areas as kind of domain experts, basically. So I think it really depends what in-house talent they have. And you just can't predict what in-house talent somebody else has. So I'd say yes, but we'll see, because like I said, it's in the infancy. We just don't really know.
In terms of folks that are watching this and wanting to see how that all evolves, because I'm thinking about the work that Trailer Bits have done, like the Cyber Grand Challenge and all of those sorts of adversarial AI, very kind of offense defense focused events. Do you have any places that you can point the audience to kind of bone up on that? I've got a follow-up question around your own bug hunting as well, but just on that part.
I would say any kind of machine learning, if you're new at this, DataCamp is the place to go. It is the best way, I think, as someone who's done looked at a few things, to learn it. Because if you pick up one of the academic textbooks, they do not start at the important parts. They start at the statistics, and they completely only focus on that. So it's looking and finding those places where you can kind of find the practical uses of AI. I would say DataCamp is a great place to start. From there, it would be Kaggle, getting involved, seeing what data sets are available, practicing. A lot of practice before you can then start to build up models that might be adversarial and attack and defense.
For sure. Okay, cool. And yeah, the follow-on to that is, what if anything have you used ML or ML concepts in your own bug hunting? If so, that'd be great to hear about. If not, is there projects that you're aware of that you can point people towards?
Yeah. So I'm working on a few tools at the moment. I'm not sure how much I want to say, not because I want to keep it secret.
Yeah, that's okay.
I don't want to promise
progress.
anything. But some of the cool work I'm working on at the moment is looking at ways to predict which vulnerabilities are going to become bigger. So if we think about how vulnerabilities work, we kind of get a curve almost, right? If we're looking at SQL injection, as soon as developers start to defend against SQL injection and not just leave it in there, or they update their software, we see it go down comparatively. And we can probably plot that curve for other types of vulnerabilities. So what you could do is you could figure out when something's at the peak of its curve and when it's just rising up and it's just becoming the next big bug. And some of the other stuff I'm working on is about recon, and especially the APIs that use normal human words, and looking at ways you could, for example, look at the marketing text of a website and figure out what their API endpoints might be, because they've shown off all of their features in their lovely paragraphs of text with their lovely
or the inverse of that, and the CSS is just a little bit janky and there's a few typos, which kind of suggests some poor code quality underneath the hood.
There's so much stuff you can do, but that's some of the stuff that I'm working on. I'm kind of working on a suite of tools at the moment to kind of do a bunch of the AI stuff. I will release it if it's operationalizable. I'm not promising anything at the moment, to be clear.
For sure, but stay tuned.
Stay tuned.
It's still exciting either way. Even putting that thought, maybe not releasing, but it refines it for a future something else. I think it's awesome.
Yeah.
There's
So we've got
awesome.
one more from Discord, which sort of fits into the recent chat. Do you think machine learning could watch your back at all when you're conducting an engagement, or alert you maybe when the blue team is onto you? They've seen your payloads and blocking your access. Do you think there's anything that machine learning can help in that area?
So I have a kind of general answer to a lot of questions when people say, can machine learning do this? If there is data and if there is an algorithm that can match that goal, so if you're asking it to just classify something like, is this likely to get caught or is it not likely to get caught? Or is this a sign that somebody's caught us? For example, we're really looking at a classification problem. If you can boil it down to having the data and knowing which algorithm will solve it, machine learning will be able to do it. The problem is, will it be able to do it well? And I think that's a really big kind of research question, really, not just for when we talk about bug hunting, but research as in academic research as well, that we don't necessarily know the answer to that. It's ongoing. It's still something we can look at.
Yeah, that's fascinating. Thank you very much, Katie. The whole presentation was amazing. I learned a lot and learned that I know nothing in this space. So it was absolutely fantastic.
Yeah, very much so.
Yeah, I'll definitely have to rewatch it probably 4 or 5 times to pick up all the stuff I missed. But no, that was
fantastic, Brahma.
Thank you.
Thank you.
And just a reminder, everyone, that we are in the Discord. Let's make sure we give Katie a huge virtual round of applause, and a nice shirt too, by the way, Katie.
Very cool.
See you repping the Level Up shirt there. Rocking and rolling. Thank you so much.
Thank you.
There we go.